Hi, my name is Benedikt Mersch, and I want to present how we can build volumetric beliefs that model our dynamic environments using map-based moving object segmentation. First, let us have a look at a dynamic environment as shown below. On the left, we have a parked static car in black, and on the right, a moving cyclist in red. In order to safely navigate in such an environment, we first want to build a static map which allows us to, for example, do online path planning. And second, we want to segment these moving objects to track them over time and then predict what they're doing next. However, previous methods usually restricted themselves to a limited sequence of path scans. So here on the right, you see the same scene, but now the color indicates the different timestamps. And this idea requires that the object is always visible in the sequence. So if you think about, for example, occlusions, this does not hold anymore. And the same happens when, for example, using sparse sensors or sensors with a limited field of view. Therefore, we propose in this work to use a local map instead of a sequence. So we do not want to restrict ourselves to this limited number of scans. And this is how we do it. On the left, you see the input to our approach. We have our current scan and a local map. So this local map consists of all past received scans in our environment, already in a common coordinate frame. And the same map is also used for the odometry. We then take scan and map, we assign a timestamp, we voxelize these, and then only keep the non-empty points to obtain a sparse 4D point cloud. Then we pass this through a sparse 4D CNN, which has an encoder-decoder architecture. It's basically off the shelf. And then obtain on the right-hand side a moving object confidence score for each point, both in local map and the scan. You can see that we are now able to also segment these traces coming from the moving objects in the local map. What is the advantage of having such a map-based MOS? So now we use the full past information we have available, which usually leads to better results, as can be shown later. And we can now refine the segmentation because of our predictions for the local map. So below, you see an example. Here we have our static, so the points which are predicted to be static of the scan in blue, the map points that are predicted to be static in black, and our moving predictions in red. At time t, our approach does not yet segment this object to be moving, although it is. But after 1 second, we gathered more observations, there are more points in the map, and now our method successfully segments it. Now the remaining question is, how can we use this new knowledge that this is a moving object? How can we fuse these different predictions? In order to do that, we propose a volumetric belief that models our dynamic environment. Below you see this belief, so we voxelize our space, and now each voxel has a state that determines if the voxel can be occupied by dynamic objects. And we use our predictions for scan and map at the top to update this belief. Here, the red points at the top are the moving predictions, and then the blue and black points are the predictions for the scan and the map, which are static. We, for each point, index the corresponding voxel, update the state using a binary base filter, and this also allows us to, for example, reject false positives, as you see on the right. So here, our belief about the voxels at the ground is already quite certain due to previous predictions, such that this false prediction on the scan does not really change the belief. You can see some qualitative results. So we trained our approach on the semantic kitty dataset and then tested on a different sensor, on a different car in Bonn. And you can see that our approach segments the moving objects successfully, even though they sometimes stop in between. This is because we use the local map with all information available. And we can also segment the objects independent of their class or their size and so on. We also carried out some quantitative experiments. Here all methods are trained on the semantic kitty dataset, on the training sequences, and then we test them on kitty tracking, which is a very busy kitty sequence, and on Apollo, which uses the same sensor but a different environment. First, you see the top two approaches use a range image, and they do not really generalize well to the Apollo data. And our approach, so the two below, is on par or even better than the previous method 4D MOS. Plus you can see that using our belief, so integrating more observations for 1 second in this case, and updating the belief and then querying the belief, always improves our results. Lastly, I would like to show you an application, which is static mapping. Here we have again 2 datasets. At the top is Livox data, which is very sparse and irregular sensing pattern, and below the previously mentioned kitty tracking sequence. If you now integrate the raw scans into the map, you will see that there are a lot of traces from moving objects, and it will not really be possible to use this map for path planning. When using 4D MOS and then cleaning the scans before integrating them into the map, we can already remove most of the traces and artifacts, but there are still some remaining. Plus we, in the Livox case, also remove static parts. So that's because 4D MOS has some false positive predictions here. When using our proposed approach with our belief, we can almost completely clean the map, and you can see that this map is now well suitable for online path planning. To summarize, we proposed a moving object segmentation method that is based on a local map using all past information. We proposed a volumetric belief that allows us to fuse these different predictions and to do static mapping. And finally, our approach is easy to use, so if you have the Minkowski engine installed for the sparse convolutions, you can just git clone our repository, make install, and then run the pipeline using our pre-trained weights, which are available on most common data formats. So binary, PLY, PCD, back files, and so on. Just try it out. And then with this, I would like to thank you for your attention.